Hello. Previously, we have looked at a demo of Contam model. We set up a simple simulation and simulated the CO2 concentration in a suite. Here, we will see how we can use the model to assess some mitigation possibilities. So, we will have the problem as follows. We will have a small suite of 20 meter square area and 3 meter height, and it is situated in a congested building. The airflow into the suite is maintained at 0.5 air changes per hour by means of mechanical ventilation. So the airflow in the suite is maintained by means of a mechanical ventilation. Currently the suite has 0.5 air changes per hour. So if we look at this, the volume is 20 multiplied by 6. So we can just already start this. Volume is basically 20 multiplied by 3. So this is equal to 60 meter cube. Air changes of 0.5 hours would mean Q is equal to 0.5 into 60 equal to 30 meter cube per hour. So we have our flow value here. One occupant stays in the suite and generally occupies the suite between 10 p.m. and 7 a.m. and then again between 5 p.m. to 8 p.m. So that is one thing. The outside air is not very clean, and PM 2.5 concentration in ambient air is approximately 50 micrograms per meter cube. The ambient CO2 is 400 ppm. Now, assuming an adult releases CO2 at rate 18 liters per hour, which comes out to be around 0.005 liters per second. The PM 2.5 has to be brought below 12.5 micrograms per meter cube and indoor CO2 to below 400 ppm. The only two manipulations can be on the mechanical ventilation systems. It can install filters and the flow rate can be changed. So we have to suggest the modifications. So now we will look at this problem using the Contam model and see what can help us achieve these conditions given the present ventilation and given the occupancy situation and the volume and the ambient concentrations. So we will address this using Contam. So we are at our Contam user interface now. So as previously, we will define our project now. So we will go to File and we will go to Project Description and we will name the project as Indoor Air Quality Control Test. Okay, let's do Indoor Air Quality Control Test. So now we have the indoor air our project description defined. We will have go to View, Project Option, and we are going to set up our flows and configuration. So units, again we will retain our SI units. Then in units of flow we will go to meter cube, standard meter cube per hour. Then sketchpad dimensions we will go. So we will modify the dimension of this sketchpad. I want little bit more white space, so I am going to go ahead and make the width as 120 cells. Height we will keep as 58 cells. So I have more. Then the next thing is edit level data. So what are we going to have? We have one level, yes. Units are meter, elevation 0, and distance to level above 3 meters. So our height is basically 3 meters, which is as we had in our problem. So this is all good. We can retain this. No need to change. The next, we have to specify our ambient. So I'm just going to go to a corner here on this left, do right click and select ambient. So my ambient is also now selected. Now we need to define our suite. So we will go to this bar and check boxes, draw boxes, and in this some area in the middle I am going to make the box. So I dragged it, click. Now I have a box. Now I have to assign it a property. So as we know, we have to assign this as a zone, which is our indoor environment. So I will right click and define zone. Now this thing is being blinking, this dot or square thing. We will just double click on this and comes the zone. So our zone name is suite. It is on level 1, yes. The floor area we are given is 20 meters square. Once that is done, the volume 60 meter cube, it is already calculated automatically. Contaminant data, we have two contaminants this time. We have CO2 and we have PM 2.5. But we have not yet defined the contaminant in the model space. So we will come back to this. So our zone is defined suite, temperature is constant, suite level 1, volume 60 meter cube, area 20 meters square, height 3 meter. So we are done with the description of the suite in terms of the volume. The next would be defining the contaminants. So we have, for defining contaminants, we will go here to data, click and come to contaminants. Right now there is nothing, so we will add. So we will click on new. The first thing we will add is CO2 is our first contaminant. So CO2. The molar mass of CO2 44 grams per mole, which will be the same as 44 kilograms per kilomole. So 44 I will add here. Then we don't have to change anything else except here default concentration is outdoor, we have ambient as 400 ppm. And we have to use this in the simulation. So defined gas CO2, molar mass and default which is ambient concentration 400 ppm. So okay. Yeah, no problem. Just click OK. And we have our CO2 there. Next, we need to have a particulate mass, PM 2.5. So let us just click new. And for now, we will only address PM 2.5 and assume everything is PM 2.5. That was given to us, PM 2.5. So species property, we will put PM 2.5. We don't need to put any molar mass. We will go to mean diameter and choose micrometer as 2.5. Mean diameter 2.5 micrometers, and effective density, okay, just effective density will be 1000 kg per meter cube. Okay, default concentration we are given is 50 micrograms per meter cube, the ambient concentration, which becomes our default concentration. So we have PM 2.5 defined, PM 2.5, then mean diameter 2.5 micrometer, effective density 1000 kg per meter cube, and ambient, which is this default ambient, becomes 50 micrograms per meter cube. Using simulation, yes. Okay. So we have two contaminants defined. Contaminant summary, total number of contaminants 2. So okay, our contaminants are defined. Now we had two sources. We had two sources in that. One was the indoor source for CO2 and outdoor to indoor sources for both CO2 and particulate matter. But in terms of like extra source, the particulate matter and CO2 from ambient will come through the flow. The individual source is our occupant who is emitting CO2. So we will go and right click inside and we will go for source/sink. So now this area is highlighted. So again I will double click here. Source sink element. So right now there is nothing here. So we are going to define a new element. And we have been told that the emissions are emissions from the occupant are 0.005 liter per second of CO2. So we will have constant coefficient as occupant CO2. The generation rate is in liter per second. So liter per second 0.005. 0.005 liter per second, which is equivalent to what we have given into 18 meter cube, 18 liters per hour. So this is okay. Adult CO2 emissions are in the range of around 8 to 20 liters per hour per person. So our value is 18 liters per hour, which is within this 8.5 to 21 or 22 liters per hour range. So this is okay, 0.005 liters per second. Of course, when a person is sleeping, the rate may go down, but for now we will keep this 18 liter 0.005 liters per second as the sort of average emissions over the whole day. So our occupant CO2 is defined, but we have to define its schedule also, because the occupant is not occupying the suite for all the time. The person is occupying the suite only under certain periods. So we will create the schedule for this occupancy. So new schedule. We will have occupant. So we will do schedule. So our occupant schedule, right now there is no available, we will create one. So we will do occupant indoors only between 10 p.m. to 7 a.m. and 5 p.m. to 8 p.m. So at midnight the person is available at 7 a.m. the person goes away. So at 7 a.m. the value becomes 0. So we have entered 0. The person comes back at 5 p.m. So that is at 17:00 hours. So we will replace this time to 17:00 and the value becomes 1. The value will become 1. Yeah. Then the person goes out again at 8 p.m. So that is 20:00. Person goes out and then comes back at 10 p.m. So at 10 p.m. the value should become 1 again. So 22:00 and value is 1. So to confirm that what we actually intended has been incorporated, we can click the button display graphically, and here it is. At midnight, full occupancy 11111. Then at 7 a.m. the occupancy goes to 0 because the person is away. From 7 a.m. to 17:00 hours, that is 5 p.m. the value keeps on 0. At 5 p.m. it increases again to 1, and then from 5 to 8 p.m. the value remains 1. Then 8 p.m. comes on 0. So the person is out for 2 hours between 8 and 10 p.m. So between 20 and 22 it remains 0. Then again goes to 1 and then remains 1 until the next day 7 a.m. So the schedule is okay. So we will say okay here. Now this occupant schedule we have to give it to the person. So we will use our available schedule and assign it to the resident's schedule. Again we can double check. So yes, it goes down, then remains until morning, goes up, goes down a little bit in the night, again goes up. So the pattern is as we intended it to be. We'll click OK. So let us just check. Schedule, occupant schedule done. Sources sunk, occupant CO2 done. So our source and sinks from the occupant, our source CO2 from the occupant is defined. Our zone has been defined. What has not yet been defined is our flow elements. So for air change per hour of 0.5, the flow is 30 meter cube per hour. So we will define our flow elements here. So let us come to this side and click on this left wall, and now something has been highlighted. I will right click and assign it a flow path. So now we have this thing being highlighted. Let's double click here. So flow element, we will add a new element, and since we know the volume 30 meter cube per hour, we will go for a constant volume, fan and forced flow model. So that's our mechanical ventilation, constant flow volume, and I will write fan in. The design maximum flow rate is 30 meter cube per hour. So we will keep it ACH, air changes per hour of 0.5, which is 30 divided by 60. So we have defined this now. Flow path will be ambient positive from ambient to suite. Schedule, so we want to keep this always on, so I will add a new schedule, and this occupant schedule is not good because that person goes in and out a lot. So we will use, we will name it fan in, always on, and we will add a new schedule called always on. The ventilation is always on, and let us see how it is currently. Every time it is 1.0, it's all good. I will check OK. and always on. This always on schedule I will copy here. So now everything is always on. Let us check if it has been incorporated. So display graphically, everything is one all the time. So the schedule is okay for this path. Flow element is good, schedule is okay, flow path is okay. Filter not yet. We will see how the concentration is presently. Then we will check about the filters for PM or anything else. So for now I will check okay. Then we will have a flow on the other side. So I will add another flow path here. Now this is being highlighted, so we will just double click and see flow element. Now this is again a constant volume flow element we will choose. Okay, and this is fan out. And again the design flow rate we will keep as 30 meter cube per hour. Flow path we will check positive flow direction on the arrow from left to right as, or this outside going arrow as suit to ambient. Schedule we have to keep this always on, so we will use the always on available schedule and copy it for the fan and name it fan out or fan always. Doesn't matter, okay, as long as we name it properly. And let us check display graphically 1.0 every time, so it is always on. Okay, so we have the schedule there, we have the flow path there, and we have the flow element also there. So done. To account for any leakages, we will add a flow path. And we will add a flow element which would be leakage. So let us name this as leakage per unit area. Let's say 1 centimeter square per meter square. Everything else we will keep the same. Flow path upward from suit to ambient, and then schedule we will keep this leakage always possible. So we will keep it always on. So leakage always on. Let's check display graphically every time it is on, so that's good. So this is done. Let's see the zone. Now zone we had also this contaminant data which we have not specified, or the initial concentrations have not been specified. We want everything to start from 0. So contaminant CO2 initial concentration 0. Contaminant PM 2.5 also initial concentration 0. So detailed zone schedule we don't need to change anything, but the initial concentrations we have changed both as 0 and 0. So our zone data is also done. So now we have defined our zone, we have defined our flow element, we have defined the leakages, and we have also defined the contaminants and the source. So now we are basically done with the setting up of the simulation, all the parameters that are needed for simulation. So next we will go and do the set simulation parameters. So airflow we will keep at transient, contaminants also will keep at transient, the integration method we will keep as it is, this also as it is. Transient simulation start from 1 and we will stop it at January 7. So again 1 week of simulation we will conduct. Then weather, output, these things we will keep as they are in the default. So the run is complete. Now we will go ahead and do the simulation, run simulation. So project file we will say indoor air control. Now it is ready to run. We will do start simulation. It ran very fast. Okay. So again let us just check the flow rates are fine. It's about 30 meter cube per hour. This is also 30. Here it is negligible flow, so the flow rates are balanced, our ambient to inside, inside to ambient. Our zone contaminants fine. We are going to now plot the contaminants. Let us see what they come out to be. So contaminant CO2 ppm, level zones to plot, suit level 1 suit, okay. Results available from January 1 to Jan 7. Then we have to do plot results from January 1 to January 7. And we will do plot data. So here we see there are trends. From 0 to 7 the person will occupy, then go away at 7 p.m. Then the person stays out until 5 p.m. Then from 5 to 8 the person again comes in and CO2 starts to rise. Then the person goes out, CO2 goes down. Then the person comes in, again CO2 builds up, and the volume is 20 meter cube. So our overall CO2 concentrations are going as high as 1000 ppm. On the x-axis we have time of day of each day, 7 days, and this is the CO2 concentration on the y-axis. So we see two patterns. One is more increase between 10 p.m. to 7 a.m. when the person has come to sleep, or in the night. Then 7 a.m. person goes out to until 5 p.m. the concentration goes down. Person comes back at 7. The person comes back at 8 p.m. so concentration again increase. Then the person comes back at 5 p.m. then the concentrations again increase until 8 p.m. when the person goes away. Until 10 p.m. concentration decrease. The person comes back at 10 p.m. the concentration again increase. So okay, the trend is okay, and the level high values are 1000 ppm. Our goal is to bring them below less than 600 ppm. We will also see less than so our goal is to bring them to less than 600 ppm. Okay, so this is for CO2. Now we want to also plot for PM concentration. So let us define this. I am just going to shrink it a bit. Okay. So now let us do the PM concentration. So here we have the contaminants to plot. So instead of CO2, now we will choose PM 2.5. Everything is the same. We will plot results from Jan 1 to Jan 7. Plot data. So we see that the indoor PM is always now 50 micrograms per meter cube, because the only source is ambient air from outside. It comes to the ventilation, the equilibrium is reached very fast, the steady state is reached very fast, and the concentration remains 50 micrograms per meter cube. Whereas we want it to be around less than 12.5 micrograms per meter cube. So both things we have to manage. So okay, we will do done. Now the two options we are given is either we can put filters for particulate matter, or we can use modify the air change per hour. So we have the option of increasing the airflow rate. Now filters, PM filters will help us remove particulate matter, and the air change rates will help us remove the CO2, because the source inside the CO2 is strong. So if we had more outside air coming in, because our outside air is 400 ppm CO2, our inside air actually is going between 400 to 1000 ppm. So our inside air is, because of the inside source, our inside air has more CO2 than outside air. Therefore flushing of indoor air might be good for CO2. For PM, the only source is outside ambient air. So if we can install filters that will remove the PM, we should get less PM indoors. But then the question is, which filter? Are we going to do HEPA filter, or are we going to have a MERV4 or MERV6 or MERV10 filter? So we will create all these scenarios now. So first we will look at CO2 only. So first we will look at PM. because the flow rate will remain the same. So let us say first we will keep the same flow rate of 30 meter cube per hour, and then we do try 1 pm. But if we want to achieve both, then for CO2 we have to reduce the flow rate, increase the flow rate. So it may or may not help PM, because PM is always influenced by the outside air, but keeping the same flow rate will definitely not help CO2. So first we will increase the flow rate and try to bring the CO2 down. So let's say we will go for view and normal mode, and click on this flow element. So I am going to introduce a new element of constant flow, and it is fan, we'll say new fan 1, and let us do 2 times the air flow rate. So we will increase from 0.45 air changes per hour to 1 air change per hour. Description: air changes per hour increased from 0.5 to 1.0. Okay, and maximum flow rate remains 60. Flow path ambient to suit is okay. Schedule fan in. What's this schedule? Let's check. It is always on. So the schedule, everything is fine. Only the flow element we have changed to a new flow element. Similarly, we will have to do this for the outgoing flow. So here also we will say new fan out 1, and flow rate we will go for 60 meter cube per hour. Flow path is the same. Schedule, let's check the schedule. Always on. So schedule is fine. So now we have basically just made the air flow rate 2 times than it was previously. Let us just check the simulation parameters. Transient, airflow is transient, contaminant transient. Transient simulation start January 1. Transient simulation stop 7 January. Okay, we will run the simulation. Okay, start simulation, close. So flows are fine. Let's plot the contaminants. CO2, level 1, suit. Results available from Jan 1 to Jan 7. Plot results from Jan 1 to Jan 7. Plot data. So we have improvement from from 1000. We have come to concentration of around 700 ppm as the maximum. Let us see even more now. So twice the capacity of fan led to quite a bit of reduction, but we want even more reduction. Let us see if it helps PM. Since PM was already only influenced by outside, it won't be influenced. PM will still go to 50 and remain at 50. But CO2, since CO2 we need flushing, the CO2 has decreased, the highest CO2 has decreased to 700. Let us try to bring it down to 600 and 500 and see. So, okay, having air flow rate of 60 meter cube per hour or 1 air change per hour brings the concentration to 700 ppm, which was good but not enough. So we need to have more airflow. So now we will go and first we will change to normal mode, and instead of this fan we will try another new fan. Let's say new fan 2, and let's make the airflow from 1 changes per hour to 2 changes per hour. So it will be 2 times 60, or 2 changes per hour becomes 120 meter cube per hour. So we have 2 changes. So 2 multiplied by 60 equal to 1. Flow path schedule are all fine. Then we have to also change the flow on this side. So let's add one more element. It's be new fan out 2. And the flow rate again we will keep as same as the inflow, which is 120 air changes per hour. 120 meter cube per hour. So we have modified our flow further. Just as a check, we will check our simulation parameters: airflow transient, contaminants, transient, simulation start 1 January, simulation stop 7 January. Okay, you can run the simulation. Start simulation, simulation status done. So we'll close and check our plot contaminants. Again, as before, CO2 we will plot. Results available from Jan 1 to Jan 7. Plot results from Jan 1 to Jan 7. So 2 changes per hour have led to concentrations of 550. 550 ppm max. So 2 changes per hour actually exceeded our requirement for bringing the CO2 level down to 500. Will it change PM? No, because PM is not influenced by indoor source. Only it will come to an equilibrium or a steady state and still remain 50. But we have made improvements in CO2. So let us keep this as 550, or we can bring it down to 500. So let us try to bring it down to 500 also. So we will go again to view normal mode, and we will add a new element called new fan 3, and let's do 3 changes per hour, which is a good flow. So we will use a new fan, 180 meter cube per hour, and here also we will use a new element, new fan out 3, with design flow rate of 180 meter cube per hour. So just for a reference, I have also added what calculation were done. Let us just check. The flow is always on, so all this is good. So again, simulation transient, airflow is transient, contaminant transient, start Jan 1, stop Jan 7. So this is fine. We will run the simulation. Flows 180, 180. Okay. Now we will plot the contaminants. Let's do CO2. Dates to plot Jan 1 to 7. Plot results from Jan 1 to Jan 7. So now we can clearly see we have reached with air at 180 meter cube per hour. The concentration are 500 ppm or lower. We can probably achieve more, but let's keep it like this, or we can optimize and have a less strong ventilation. but we can just keep it like this. So for 180 meter cube we are satisfying very well as and maybe exceeding, so we are even actually reached lower or equal to 500 ppm. So let's keep this flow rate, so I'll keep it done. But what about PM? PM is still 50 and PM we want 12.5. So certainly influencing the air exchange rate is not helping PM in any way. For PM we should try then some kind of filtration. So we will look at that next. We will keep the flow rate at 180 meter cube per hour, and now we will start looking at filtration. So first I am going to again go back to the normal mode view. Now if you recall, our filtration was in the flow element. So I am going to go to the flow element on the left, because this is where the inflow is coming. So I am going to go left, and let's keep this new fan 3 and add a filter. So we will add a filter element here. So we will add a new, because there's nothing here, let's add a new filter. Anything is there? Nothing is there. So we will add a new element, and we want to have a particle filtration. So we will choose simple particle filtration. So name. Now different filters have different particle efficiency. Let's try to save cost and go with the MERV5 filter, which gives 20% efficiency. So let's say area remains 1. Let's make area 2 meters square, and let's see if we had some area here. No, only flow rates were there. So let's have a filter area, simple particle filtration, MERV5. We will keep the area as 1. Let's keep it 2 meters square, or we'll keep 1 meter square only. Depth is fine, this we don't have to touch, but we have not included the efficiency yet. So let's see edit elemental data. Now you see this console, this window, filter curve data, particle size and efficiency. So actually this model wants to have a filters efficiency curve, which means we have to give more than 1. If we only give 2.5 micrometers and say efficiency, MERV5 efficiency is 20%, so 0.2, and add, and if we try OK, it will say particle filter element requires at least 3 data points. So 2.5 is 0.2 or 20% efficiency. We will add some more. So we will have 1 micrometer also at 20% efficiency, and let's have one at 5 micrometers also at 20% efficiency. So now you see how the model is going to take the efficiencies: particle mean diameter on x-axis and filtration efficiency on y-axis. So it's maintaining 20% or 0.2 efficiency for all the particle filters. So let's click OK. MERV5 data is done. So we see we have included MERV5. Now let us add new elements. Simple, because we are not sure MERV5 will be enough or not. So let us try MERV5, MERV9, MERV12 and also HEPA filter. So now we will add, let's say MERV9. Everything remains the same. Description would be 30% particle removal efficiency, or 30% we will say PM 2.5. And again as before we will have 1 micrometer, 0.3, 2.5 micrometer, 0.3 and 5 micrometer. So now we see efficiency of everything is 0.3. So okay. Filter element must have data defined. Oh, it didn't say. So 1, 0.3, then 2.5, 0.3 and also 5 as 0.3 and okay. So you see there are two options, MERV 5, MERV 9. I will add a description here also. MERV 5 was 20% PM 2.5 removal. Okay, now let's try another new element which is MERV 12. MERV 12. MERV 12 gives 80%. And element data 1 micrometer 0.8, 2.5 also 0.8 and 5 also 0.8. So now you can see everything is 80% removal. So okay and okay. So now we have three options. The last we will try is also a HEPA filter. HEPA filter have a very high removal, but of course they will be much more costlier. So we will say HEPA filter, and the efficiency of HEPA is 99.97% PM 2.5 removal. And edit element data. So 1 it is 0.9997. For 2.5 also same. 5. So 99.97% removal. So all filters are there. For outflow we do not need filters because whatever air is inside will already get cleaned, and then we can just put it out, and the outgoing air after installation of filters will be cleaner than the indoor air, because right now we are not considering any indoor sources. So I think we are ready to run the next simulation. So first let us start with let's use fan 3 only. The flow element is fan 3 180. Filter we will use the least efficient MERV 5 filter, 20% PM 2.5 removal efficiency. Okay. Now let's just confirm our simulation parameters. Airflow transient, contaminants transient, transient simulation start 1 January, transient simulation stop 7 January. Okay, so I think we can run. So start simulation. The flows are still fine. Let's plot the contaminant. So results available from 1 to 7. Plot results from Jan 1 to Jan 7. Let's just confirm that our CO2 is still the same, and we find that CO2 is still as it is supposed to be, between 400 and 500, because we decided later we will keep it 500. Let us see PM 2.5. So we have got some removal, but we are at 40 microgram per meter cube. You see PM 2.5 does not go 50, but now stops at 40. So there is improvement, but not enough. So I think we need to go to a better filter. We will go back to the normal mode and double click, and we will change the filter now. So instead of MERV 5, let's try MERV 9, which gives us 30% PM 2.5 removal. Okay, and okay. We'll just double check the simulation parameters. Airflow transient, contaminant transient. Okay, all good. We will run the simulation. Simulation stops. Plot the contaminants. Single contaminant. Zones to plot fine. Results available from Jan 1 to Jan 7. Plot results from Jan 1 to Jan 7. And we'll plot data. CO2 again as expected, no change. Let's see PM 2.5. So now PM 2.5, our highest is going to be 35 micrograms per meter cube. So we are steadily coming down, but we are not there yet. So let us try to go heavy, like let us try to be do the best possible filter that is allowed. Because we are not buying the filter, we can do this thought and testing on the computer model itself. So let us try to go for the HEPA filters. So we will go for our view, normal mode. Filters, we will edit and make it now. 12 we will check later. First we will make HEPA filter. So okay. And let's to check simulation setup. Transient. Simulation start 1 January, simulation stop 7 January. So okay. We will run the simulation. Start. Simulation is over. Let's plot the contaminant results. We know that CO2 is always the same pattern as before. So we will plot PM 2.5 now. And dates to plot, results available from Jan 1 to Jan 7, plot results from Jan 1 to Jan 7. Oh, so when we install PM HEPA filter, if we do look at any time of day, the PM concentration is basically 0.015 micrograms per meter cube. It is way more over designed. That our goal that was to bring it around less than 12.5, maybe around 10 or so. So this is too much control, and we probably did not need that. And HEPA filters of course are also more expensive than any less efficient filters. So in this case we do not need to go as low as a HEPA filter. So let us try to become more optimized. So let us try. One more option is left, MERV12. So we will go and check the MERV12 now. First we'll go to normal mode. Now we will go to flow, we'll check our flow path, and we will go to filters, then edit filter, and HEPA not good enough, or HEPA is too good actually. So we will go for MERV12, 80% PM 2.5 removal efficiency. So everything else is the same. We will do MERV12, 80%. Set simulation, airflow transient, contaminant transient. Okay. This console is come. Start simulation. Stop. Flow rates are still all good. Let us check the concentrations. So we know CO2 is not going to change anything. We'll do PM 2.5. The results available from Jan 1 to Jan 7. Plot results from Jan 1 to Jan 7. So this is good. From 50 using a MERV12 filter, which gives 80%, so it is not as efficient as HEPA filter, but HEPA filter are anyways too efficient for our application. For our application, MARV filters are better. Also HEPA filter, we can say ki okay, install HEPA filter, it gives clean air, but they have to be replaced again and again. So in this case, it looks like our MERV 12 filters will do the job for us, because the concentration of PM 2.5 is 10 micrograms per meter cube, and it is not changing. So CO2, if we go 180 meter cube per hour, our CO2 is 500 or below. And if we go 120 meter cube per hour, our CO2 is 550 ppm. And if we go MERV 12, our PM 2.5 becomes 10 microgram per meter cube. So this is how we can check or we can estimate the effects of different options. So in our course, since we are only looking at the scope of the model is introduction and how it works and how it relates to our theoretical mass balance that we have done. As I said previously, Contam itself is a full course probably. So, but even with all that considering, with this model that we have set up even for a single suite, we are able to analyze so much. We were able to design our air exchange or air change rate or the flow rate, and we were even able to identify which filter we need to install to bring our indoor air quality with respect to PM 2.5 to the desired level. So even in this stage, this model is very helpful. This can guide anyone to make a better and even optimum design. As we saw, the HEPA filter was not required. A MERV 12 filter was good enough. So this kind of work even helps us optimize the design and even the cost part of the whole indoor air quality mitigation measure. Right? So this tells us about different contaminants. When we are looking at filters, in fact, it is even possible, if we were to make a new filter, let's say a new element, we can even have gaseous filtration. So it's even possible to have a gaseous filtration, and we can possibly apply it to CO2. Let's say I will say CO2 filter, maybe, or just as an example we are showing that even in case it was not CO2 but something else we wanted to remove, some VOC. I will name it VOC filter and then I will filter CO2 or whatever. If we had a VOC filter, we could have do a efficiency of here and be able to model the CO2 emissions VOC reductions also. Likewise, we have so many options for sources and sinks. Pressure deviant force, cutoff concentration, we have a decaying source, burst source, deposition velocity, deposition rate, super source. So there are many possibilities in this model. So the user, anyone who is interested in indoor air quality application, would be highly encouraged to look at this kind of model or even other similar models that have this kind of capability. And if we see, these models almost always very in a good way, they draw from the mass balance, simple mass balance models that we have learned or looked at earlier, and then we can add more details, more complexities, and even in simple scenarios we can see how they are useful. So from the results of the model, we find that for PM 2.5 removal, a MERV 12 filter would be sufficient, and HEPA filter would not be actually required. For PM removal, the results were also sort of independent of the high flow, because for CO2 we saw 180 or 120 meter cube per hour was required, but for PM it was not dependent because the source of PM 2.5 was air, not really an indoor source which required flushing and was dependent on the flow rate. So this is one example, at least for PM 2.5 filtration, where Contam was useful in choosing the appropriate filter without the need of any experimentation. For CO2 removal, we had the indoor source, and that increased the concentration to above the ambient level. In our case, the particle filtration did not affect CO2 because CO2 was gas and we defined the particle filtration efficiency only for the particle form. So that did not have any influence on CO2 concentration, which makes sense. More airflow rates, 120 to 180 meter cube per hour through the suite prevented the buildup of CO2 in the air and kept it below 600 ppm and led to the decrease in the maximum CO2 level that was achieved in the suite. So in this case again we were able to define and if one wants, one can have like even a more fine-tuned airflow rate, which will help one to design the airflow that CO2 just touches 600 ppm, because maybe 140 would have been optimum. So with several runs of the model, one can in principle even get to that fine level, and in this way this model helps us to define our flow rates, because now we know that a ventilator that gives 300 meter cube per hour is not required. If we go above 120, it will suffice our purpose to come below 600 ppm for sure. Likewise, for PM 2.5, a MERV 12 filter was sufficient. We do not need to go things like HEPA filter or even something more than MERV 5. So in addition to helping us design the airflow rates and the filtration mechanism, it also helps us to optimize that we do not over design in a way without any mathematical or computer modeling information. So in this way Contam had been very useful, and of course there are a lot of applications of this model which the user can take up as they go. So as I said earlier in one of the earlier parts, Contam can be used for the quantitative analysis, optimizing the ventilation strategies, and assess the effects of installation of filters. Overall, it can help in basically designing of appropriate flows and appropriate cleaning mechanisms or mitigation mechanisms. Contam can also help us design or understand the airflow such as infiltration and exfiltration, and the room-to-room airflows by the mechanical means, wind pressure on exterior of building, and buoyancy effects by the indoor-outdoor temperature differences. So this we have looked at before, so I will move through them a bit quickly. Then Contam concentrations can also be used to study the sources, dispersal of airborne contaminants via transports and flows, contaminant transformation by reaction, adsorption and desorption to building materials, filtration, deposition to building surfaces. So we can study all of these things for the different contaminants, and one can do the personal exposure part. So if we were to now summarize the course, we have looked at the many aspects of indoor air quality. So like what kind of chemicals are possible to be existing in a house. So like again we will come back, we have VOCs in the personal care products, VOCs and SVOCs. So we have also studied about VOCs, SVOCs and the chemical reactions that happen inside the house. At least we have looked at them. In bathroom we have mold and mildew. So we have covered some aspects on bioaerosols and bioaerosols measurements, sampling and analysis. Then again we have our air fresheners, candles, perfumes leading to VOCs. Then we have mechanical ventilator, which can remove, in this case, the pollutant, or it can help flush, increase the ventilation rate, or it can bring clean air if the incoming air passes through a filter. Then we have NOCO. We have surface deposition of pollutants. So we have looked at some aspects of deposition of aerosols in the indoor air as well. Then we have gas stove cooking. So we have looked these aspects of emissions. Same for fireplaces. Cleaning products we have looked at, and we have looked at the chemicals that can come out, predominantly VOCs. And we have exchange, so we have looked at air exchange with the outside also, outflow and inflow. And we have looked at different aspects, CO2, virus, dust, bacteria, allergens. So we have done cancer risk assessment, non-cancer risk assessment, and also quantitative microbial risk assessment. So again, we summarizing everything, we have like so many sources in all the parts of the building. In attic we can have asbestos, fiberglass, dust and dust mites. In home office we can have like computers, printers, photocopiers that will emit VOCs and ozone. The furniture maybe can emit VOCs and formaldehyde. Then we have the living room, where we can have fireplace, dust mites, allergens, second-hand smoke, pet hair. We can have carpet acting as a source. Now we have garage, where we can have CO, carbon monoxide, other gases. Solvents may be stored, pesticides and herbicides may be there, dust, paints and chemicals. In kitchen we can have odors, VOCs, cooking pollutants as well as bacteria. So we have some idea now how to sample all of these and analyze all of these, and also in some ways control all of these. In bathroom we have humidity, aerosols and sprays and molds. Bedroom we have allergens, dust, carpet related emissions. And then they have the basement, where we have a lot of humidity, unpleasant odor, molds, solvents, dust mites and other chemicals, which we have also looked before. So we have covered about everything, including what they are, how they are measured, how they may be controlled, how they may be, or how the indoor air, how the indoor environment may be designed to reduce these kind of exposures from these contaminants. So we eventually covered in week 1, we studied what were the more common air pollutants, what were the sources of these pollutants, and also we looked at the methods to estimate emissions. Then in week 2, we looked at the methods to conceptualize the indoor air pollution problem through mass balance models. We studied how to structure these pollution problems and how to use simple mass balance and first order rate constants to determine time variable and the steady state concentrations given the emissions. Then we looked at the concept of residence times, sources, sinks, losses, lifetimes. In week 3, we looked at outdoor sources as the outdoor air as the source to indoor air pollution, and the indoor-outdoor IO relationship and what it means. We looked at the importance of air exchange and ventilation rates. Then in week 4, we looked at aerosol basics, because PM is an important component, and we also have secondary aerosols being formed. We looked at how these fates are possible: deposition, condensation, coagulation processes. what were the sources of these aerosols and the respective aerosol properties. In 5, after these physical aspects, we looked at the indoor air chemistry. What were the common pollutants? What are the basics of these reactions? We looked at a little bit about surface reactions and some examples. Then after the physical and chemical aspects, we looked at bioaerosols, sources of bioaerosols, and the health impacts and the environmental factors that may influence the bioaerosol concentration in an indoor environment. Then we had again indoor air exposure risk assessment. So after looking at the physical, chemical and biological pollutants, we did a week on indoor air exposure risk assessment. So we calculated things such as potential daily dose, average daily dose, and how we can calculate the non-cancer risk. So using reference concentrations and cancer risk using IURs. And we also did a little bit on the quantitative microbial risk assessment, which was determined by the dose of the bacteria that we have consumed in terms of colony forming units. After all this, we did methods for monitoring of physical and chemical pollutants, their sampling, instrumentation and analysis parts. After physico-chemical, we looked at the pollution monitoring for bioaerosols, sampling and analysis methods, and we had a guest lecture on comparison of some methods for bioaerosol sampling. After all that, we looked at the air pollution in the Indian context, overview and gaps, and the case studies on physico-chemical contaminants, and a case study on bioaerosols in a typical or in a specific indoor environment through a guest lecture. Then after that, we looked at some guidelines, methods of control of pollution, and we had the introduction to the model Contam, how we can set it up and use it to model different contaminants. Then we looked at the bit on the effects of indoor air pollution, focusing a bit on the sick building syndrome. Then we looked at some more methods of control of pollution, and then we looked at like examples for using models, or in our case Contam, to design the pollution mitigation, the pollution mitigation in a to be designed indoor environment. So design pollution mitigation for indoor air, and we look specifically for CO2 and PM 2.5. So in closure, I would like to tell or re-emphasize that the indoor air quality is a very important topic. Anything that relates to indoor air quality are quite important topics. So this course has provided a platform, hopefully, from which the student will be able to build up on one or many aspects of the indoor air quality. It could be physical, chemical, biological, or risk assessment, or mathematical modeling or design. And so once a student can build up on one or more of these many aspects of indoor air quality, hopefully they can take up the indoor air quality topic in more and more research and application works.